Well, good morning. This is 9:30 in the morning on Thursday, the 10th of November, 2016. It's supposed to be Math 238, differential equations, but unfortunately I'm the only one in the room right now. Trying to get the graph paper to come up, but so far it's not, or actually the blank paper says graph paper. So it should be on the way soon, but still not here. Just a couple of announcements while we're waiting for it to come up. The office hours today are changed ever so slightly. Normally they're 12:15 to 3:15. However, today not. They'll be 12:15 to 2:15 because I have a faculty meeting over in the hall building at 2:30. So I'll leave the office between 2:15 and 2:25 probably to get over there. So 12:15 to 2:15 today. Also, normally on Fridays, I have office hours from 7:45 to 11:45 on the Birmingham campus. Not tomorrow. Tomorrow is Veterans Day, so it's a state holiday. The college is closed. Nothing will be open. There will be no office hours for anybody tomorrow. So that's the update on that. So let's go to the new slide. Yeah, now we've got it done. So I don't know where everybody is, but from what I have before, we talked about factoring operators last time. We were doing undetermined coefficients annihilator approach. Kind of a mean-sounding term, isn't it? Now, how this began, when you have coefficients, AI, where I goes from 0 to n, real coefficients, real constants, not complex or imaginary. A linear differential operator can be factored whenever the characteristic polynomial factors. In other words, if R1 is a root of the auxiliary equation, and I'll write this down. Oops, let me get my pen blackened. Okay. You have this as the auxiliary equation, a sub n, m to the nth, plus a sub n minus 1, m to the n minus 1, plus dot, 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 all the way down to a sub 1, m, plus a sub 0. Now remember, these a's are real, not complex, meaning having imaginary components to them. And if that, and this is called the auxiliary equation, if that auxiliary equation has factors, can factor, then so will the this is the characteristic polynomial. Okay, if that factors, the linear operator also factors. And as they say it here, then L, which is that linear operator, is equal to D minus R1, where R1 is one of those factors. If R1 is a root of this equation, R1 a root of that equation, okay, then L could be D minus R1, that's one of the roots, times some other factor, P of D, where P is a polynomial expression in your differential operator, D, of order n minus 1. You've just reduced it by 1, okay? So in other words, you treat that differential operator as if it's an algebraic quantity. So if that was D2 plus 5D plus 6 operating on some function y, then we can take this and say that's the same as D plus 2 times D plus 3, okay? Because that's how that would factor. Now let's step back a minute and say, okay, let's say this is your operator on some function y. Okay, y is some function of x. Okay? Then this is telling us that this is also equal, and let's just take a moment here and say, what does that mean? d2y means second derivative of y with respect to your independent variable, we're assuming x, plus 5 times the first derivative of y with respect to x, plus 6y, equal to something. That could be a 0, it could be a characteristic, it could be whatever it is, that's what we do. Well, then that's saying that's the same as d plus 2 times d plus 3 times y. Which, what does that mean? That means y prime plus 2y times y prime plus 3y. Okay? Because your d of y is, that. So, amazing. Okay? A second derivative function there with a first derivative in it can be changed to be this. Okay? Factors of linear differential operators with constant coefficients commute. There's another property. You could have written that d plus 3 times d plus 2. They commute. Doesn't matter which order. A differential equation such as, let's start over and start this more from scratch now. Okay? A differential equation such as y double prime plus 4y prime plus 4y equals 0. That's the differential equation. Now, another way to write that is with your operator, d2 plus 4d plus 4 times y is equal to 0. That's what that means. Okay? Now, amazingly, this also means you could say this is d plus 2 squared times y equals 0. So now you went from being a second derivative in a function, higher order differential equation, to products of lower order differential equations. First order differential equation. Okay? And another way to write this, of course, is d plus 2 times d plus 2 times y. Okay. In case you had a doubt about that. So, your annihilator operator, sounds pretty vicious, doesn't it? If L is a linear differential operator with constant coefficients, no variable coefficients, we'll just leave it like that. And f is a sufficiently differentiable function that you can take those derivatives, such that L of f of x, where L is your linear differential operator, if this is equal to 0, then L is said to be an annihilator of the function. Okay? When you do that operation on it, you make it equal to 0. The function was at 0 before you do the operation. It does. It's an annihilator. Okay? For example, a constant function y is equal to k is annihilated by d, since d of k is equal to 0. The function y is equal to x is annihilated by the differential operator d2, d squared, since the first and second derivatives of x are first 1 and then 0, respectively. Similarly, d cubed of x squared is 0, because d of x squared is 2x. d2 of that would be then 2, and d3 would be 0. So the differential operator d double prime annihilates each of these functions. I'm sorry, that's not double prime, dn. Okay? Annihilates your constant function, linear functions, quadratic functions, cubic functions. Keep going until you get to x to the n minus 1. So if that first n was a 7, it would annihilate all functions up to x to the 6th. Okay? If it was a 3, it only annihilates constants, linear, and quadratics terms. Okay? So it annihilates all up to n minus 1. As an immediate consequence of that, and the fact that differentiation can be done term by term, a polynomial function, I think I'll go to a clean page on this one because I'm just running out of room at the bottom. Okay, here's a polynomial function written kind of in backwards order, it seems like to me. C0 plus C1x plus C2x squared plus dot 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 plus, and we'll go up to C sub n minus 1 x to the n minus 1. Okay? That function, polynomial function, degree n minus 1, can be annihilated by finding an operator that annihilates the highest power of x. In other words, d sub n. No, raised to the n, d to the n. Okay? D to the n minus 1 doesn't annihilate it completely. It comes close, but doesn't. You need that one next one. Okay? The functions that are annihilated by the linear nth order differential operator L are simply those functions that can be obtained from the general solution of the homogeneous differential equation L of y is equal to 0. Okay? Because if you think about it, that's what your L is. It's that function of your operators. Okay, I thought I saw a student coming in. Maybe not. I'm going to close the door so I won't bother people to go down the hall. I was thinking we might get somebody in by now, but it doesn't look like it, so I closed the door. They can still come in, but I just didn't want to bother other people. All right. So if you had an L of y equal to 0, okay, obviously if that was a polynomial function and your y was your L was differential operator up to degree n, then the y, as long as its maximum degree was less than n, that annihilates. Okay. The differential operator, and here's another one, d minus alpha raised to the nth. Okay. That annihilates each of these functions. Okay. E to the alpha x, e or x e to the alpha x, x squared e to the alpha x, and all the way up to x to the n minus 1 e to the alpha x. Okay? Now, I don't know if you find that intuitively obvious. I don't. Okay? But I think if you played around with it a little bit, let's just take d minus alpha to the first power and operate on that first function. Okay? Well, the derivative of e to the alpha x would be alpha, or e to the alpha x times alpha so if that was a 1 there, that would be d minus alpha operating on e to the alpha x. Okay? That would be derivative of alpha x, which would be e to the alpha x times alpha minus alpha times e to the alpha x. Obviously, that's 0. Okay? So if this d is 1, and that power of x is 0 there. Okay? Now, if you had d minus alpha squared, it would eliminate that one for sure, but also the next one. Okay? So let's do that. That would be d minus alpha times d minus alpha times your f, which is x, e to the alpha x. I'm finding it hard to write here. Okay. I'll let you proceed that. The book doesn't go into this much detail. But if you do that operation, I think you'll see that that works. Especially if you were to expand the operator and make that d2 minus 2 alpha d plus alpha squared, and use that to operate on x e to the alpha x. First thing you would do was take the derivative of this, and derivative of x e to the alpha x would be x e alpha x e to the alpha x, because it's a product rule, and you're taking sorry, having trouble breathing. The cold air is not coming in as bad this morning as it has, but still clogging up. Okay, the product rule says the first times derivative of the second. Derivative of the second is e to the alpha x times alpha. So that would be your first term in it, plus derivative of x, which would be 1 e to the alpha x. Okay? Okay. Then you also have a second derivative, so it's the derivative of that, which would be when you take the derivative of that, then you get that first alpha doesn't contribute much. Then you got exactly what you had before. Derivative of that part would be exactly what this was. There's another alpha x e to the alpha x plus e to the alpha x. Plus derivative of the second part there is just alpha e to the alpha x. So that's the second derivative of this. So let's spell that out. That would be an alpha squared x e to the alpha x plus alpha e to the alpha x plus alpha squared e to the alpha x. Okay? That's all of that term there, the d2 of that thing. Okay? Minus 2 alpha times this thing. Well, that would be alpha squared x e to the alpha x minus 2 alpha e to the alpha x. Okay? Plus alpha squared of x e to the alpha x. All right. I see an x squared e to the alpha x here and here. But here we have minus 2 alpha squared e to the alpha x. So sure enough, those add to 0. Okay. Here we have an alpha e to the alpha x. Okay, I missed a term here. Seems like I have, but I can't find it. Here's an alpha e to the alpha x, minus 2 alpha e to the alpha x. I'm wondering if this is just 1, not squared. Let me find that where I came across that. Frankly, oh, I'm sorry. Yeah, that parentheses ended there, and this wasn't alpha squared. This was just alpha. Okay, so sure enough, that was that. So now you have a plus, and a minus 2. Yeah, you got that. Sorry about that. So sure enough, that does add to 0. Okay, now I did it for 1, did it for 2. I think you can see the pattern continues. Okay. It says to see this, note that the auxiliary equation of the homogeneous equation d minus alpha to the n y is equal to 0 is m minus alpha to the n is equal to 0, and since alpha is the root of multiplicity n, the general solution then would be it's getting a little dark. I'm going to have to turn on the light. Okay. Basically, you're saying since alpha is a root of multiplicity n, okay, then the general solution has to have n terms. I was trying to see how the second thing related to the first. It doesn't, except that you have to have n constants, so n terms. So sure enough, that's fine. So let's look at example 1. Using some annihilator operators. Sorry, my throat's going on me. Find a differential operator that annihilates the given function. The A here is this function. 1 minus 5x squared plus 8x cubed. Okay. Find a differential operator that annihilates that given function. Okay. First, this is a polynomial, so you don't need the e's in there. Okay. And all we're doing is the differential operator. So basically all you have to do is note what the maximum exponent here is 3, and then say your operator just has to be d4. Okay? And that'll do it. Okay, you don't need anything else. Okay, so just D4 operating on this function, 1 minus 5x squared plus 8x cubed. That's going to be equal to 0. Guaranteed. Because your fourth derivative will wipe out the x cubes, the x's completely, and then even the constant. Okay? I thought this was going to be something more complicated than what they're asking, but find a differential operator that wipes out this, e to the minus 3x. Okay? Now, that's going to require a differential operator that is going to be d plus 3. Okay? D plus 3. That will do it. Okay? Because if you did d plus 3 times e to the minus 3x, that would be derivative of that would be minus 3 e to the minus 3x plus 3 times e to the minus 3x, and obviously that goes to 0. So sure enough, that's all you need for that one. Again, I thought it was going to be a little more stringent than this. How about this one? 4e to the 2x minus 10x e to the 2x. All right. Sorry, folks. All right. On first glance, this is a lot like the box above that contains 5 in it, and this would be d minus 2, that's your alpha here, and which power 2. Okay? Now, let's see if that works. Sorry. This would be the same as d2 or d squared minus 4d plus 4 operating on this function, 4e to the 2x minus 10x e to the 2x. Okay. Man, I may have to take a short break and clear my head if it doesn't clear up on its own. So to do this, we have the function. What we need to do is the derivative of that function. Okay, and that would be if I could write it right, it would be, it didn't erase. Sorry. That's an X. No, that's an E. I had an X and it was an E. Yeah. Okay. Sorry about that. So take a derivative of that, and that would be, derivative of that would be 8e to the 2x minus product rule type thing, 10x e to the 2x times 2, which would make this a 20x, minus 10 times 2, wait a minute, just 10, sorry, got a bit carried away there. Yuck, my pen, my eraser's not pulling up. Okay. All right, let's go back and see if I can get that to write better. Okay, the derivative of the first term is 8e to the 2x. Okay, minus and it's 10x e, and then the derivative of e to the 2x, which is 2e, so that's a 20 x e to the 2x, and then the second part is minus 10x, no, minus 10 times e to the 2x. Okay. So this gives us a minus 2e to the 2x minus 20x e to the minus 2, no, e to the 2x. Okay, sorry. Now, take another derivative of this. Okay, so this is what that is. Another derivative of this would be a minus 4e to the 2x minus 40x e to the 2x minus 20 e to the 2x. Okay, that's the second derivative, and simplifying that would be minus 24e to the 2x minus 40 e to the 2x. Okay, so when you take that derivative twice, that's what you get. That would be a minus 24 e to the 2x minus 40 e to the 2x. That's your d squared of that thing. Minus 4 times the d. Well, this was the d, so that's going to be a plus 8 e to the 2x. Okay, and you got a minus 4 times a minus 20, that's plus 80 x e to the 2x. Goodness gracious, this thing is driving me nuts. Okay. All right. Then we have finally plus 4, so that would be a 4 times 4 is 16 e to the 2x minus 40 e to the 2x. Now, I have a suspicion I've dropped a sign somewhere here, and let me make sure on that. No, maybe not. Maybe not. Okay. Let's see what we got. I know I've dropped an X somewhere. Let me see where that one is. I think here we have an X in that one. Yeah, for sure. That's what I left off there. And there we've got a minus. Alright, still finding my way here, sorry. That has one each, that has one each, and this one has, that has an X in it too. Okay, so you got a minus 40x e to the 2x, and another minus 40x e to the 2x, plus 80x e to the 2x. That adds a 0. And here we have 8 plus 16 is 24. That adds a 0 too. So, sure enough, that worked. Okay? And they didn't show it, they just said it is, and indeed it was. Now, that's if you have the single, you might say, parameter alpha that's surrounding there. So let's erase all that E. Now, what if you had both an alpha and a beta? So you had an alpha and beta, where beta is greater than 0, these are, sorry, any real numbers. The quadratic formula reveals that, okay, let's just write it down and then we'll see what it means. M squared minus 2 alpha m plus an alpha squared plus beta squared oh man I'm sorry, I may have to stop a moment. Finish this expression. Raised to the nth power is equal to 0. Okay? No, I'm sorry, nth power. My eyes are not focusing too well. Has something to do with my difficulty in breathing too, I think. So let me pause this a minute. Sorry about having... All right, I'm sorry. My head was clogged up. My throat was clogged up. I had to go clear out and drink some water and stuff just to clear my head a little bit. I'm a little better now. It's not all better, but some. Okay. We're expanding from a 1 parameter, you might say, alpha, to 2, and now the second one, b, has to be greater than 0. When these are real numbers, b being a positive real number, alpha any real number, the quadratic formula reveals that m squared minus 2 alpha m plus alpha squared plus beta squared raised to the nth power is equal to 0 has complex roots of alpha plus, here we go again, plus I beta and alpha minus I beta. Okay? Now, I don't know if you've done the math to do that yet. And by the way, both of these have multiplicity in, because that whole quadratic there is raised to the nth power. Let's take just a moment and see what quadratic formula tells us. If this is a quadratic in m, this says that m is equal to minus b, which is 2 alpha, plus or minus the square root of b squared, which is 4 alpha squared, minus 4, sorry, a is 1, and c is alpha squared plus beta squared. Okay? All over 2. A is 1. Okay? All right. Let's see what this gives us. 2 alpha plus or minus the square root of 4 alpha squared minus 4 alpha squared, that goes to 0, minus 4 beta squared. But remember, they told us beta was always positive. Okay? Well, it doesn't matter, but they told us it's positive. But whether it was or not, beta squared would be positive. And so you have a minus, sorry, yuck. That would be the square root of minus 4 beta squared, which is obviously a negative number, and that would be 2 beta I, okay? Oh, and this, by the way, is divided by 2. So this gives you 2 alpha plus or minus 2 beta times I over 2. Well, the 2's go out, and that's where you get your alpha plus I beta, alpha minus alpha I beta, okay? Beta I, whichever you want to call it, okay? Sorry. And why in the world, yeah, I just noticed that the book calls it I beta, whereas almost everywhere else says you always put the real part first and the I at the end, standard form, but why, I don't know, they do it that way. Okay, but those are roots for that, but then that traces to the nth power, so those are I in multiplicity. Okay, now, from the discussion at the end of 4.3, which was quite a ways back there, we have the next result, and this is your box here, so I think I'll start this on a clean page. If I can get it go to a clean page here. The differential operator, D2 minus 2 alpha D plus alpha squared plus beta squared raised to the, should be a bracket there, nth power annihilates each of these functions. Each of these, okay? E to the alpha x cosine beta x, x e to the alpha x cosine beta x, x squared e to the alpha x, sorry I wrote that wrong, alpha x cosine beta x, and keep dotting up there until you get to x to the n minus 1 e to the alpha x cosine beta x. Okay? Gets all those plus all these. E to the alpha x sine beta x, x e to the alpha x sine beta x, x squared e to the alpha x sine beta x, all the way up here to x to the n minus 1 e to the alpha x sine beta x. Okay. Part of my problem is it has gotten colder in here. Fortunately, the wind's not blowing directly on me thanks to closing the vents. Thank you very much. But the room is still getting pretty chilly. Number one, it's chilly outside, so we don't get much help there. But the second part being that the system is still pumping cold air in. Why, I'm not sure, but they are. All right, so we're ready for example 2. Find a differential operator that annihilates this thing. 5 e to the minus x cosine 2x minus 9e to the minus x sine 2x. Okay. Guess what? Going to be an operator that looks a lot like this one. Let's see if we can figure out what that's going to be now. D squared minus 2. Now what's your alpha here? A minus 1. So that's going to be plus 2d plus alpha squared, that would just be 1, plus beta squared. Your beta here are your 2's. So 1 plus 4 is 5. To the your n here is 0, okay? So you just need this 1. You don't need any power here. So let me clean this up a little bit. Okay. So I think that's the operator that does it for us. D squared plus 2D plus 5. All right. I hate to take the time to do it, but it seems like we need to verify that. Okay? So if this is your function y, then your y prime, I've decided to stay away from the d's, they get too confusing. Y prime is equal to product rule again, first times the derivative of the second would be 5 e to the minus x times a minus 2 sine 2x. So that would be a minus 10 e to the minus x sine 2x. Okay? That's the first part of the product rule of the first term. This may be worse than I wanted it to be. The second part is going to be a minus, minus 5e to the minus x times cosine 2x. Minus 5e to the minus x cosine 2x. That's the derivative of the first times the second. Okay? Minus the first, which, is a 9e to the minus x, just as it is, times 2 times cosine 2x. So that's be minus 18 e to the minus x cosine 2x. Okay, that's the first time derivative of the second part. Sorry. I'm awfully sorry. Yuck. Derivative of the second, which is going to be a plus, derivative of the first, which is going to be a plus 9e to the minus x times sine 2x. Okay. Now, let's, combine like terms here. Okay. The sine terms here is going to be a minus e to the minus x sine 2x. The cosine terms here are minus 23 e to the minus x cosine 2x. I hope I did that one right. Now let's do our y double prime. Take the derivative of this one, which will be the first, which we'll say is a minus e to the minus x with a 2 in front cosine 2x. Okay, that's the first times derivative of the second of the first term there. Okay, minus, it's actually going to become a plus, derivative of the first, e to the minus x times sine 2x. Okay? Now let's do the second term. First is going to be it's going to be a plus 23 e to the minus x. Let's make it 46 e to the minus x sine 2x. I changed the sign because the derivative of cosine is minus sine. The double came from the chain rule part there. And then we have derivative of the second part, which is going to be a plus 23e to the minus x cosine 2x. All right, and let's combine some of those like terms. The cosine terms are a minus 2e and a plus, so that's going to be a 21e to the minus x cosine 2x. And the sine terms are going to be a plus 47 e to the minus x sine 2x. Okay. Getting to regret doing this. Okay, so your y double prime corresponds to this one at the bottom. So that's going to be, I guess I'll write it down, 21e to the minus x cosine 2x plus 47e to the minus x sine 2x. Okay, plus 2 times the derivative, which was that one, so that's going to be minus 2e to the minus x sine 2x minus 46 e to the minus x cosine 2x plus 5 times the original function, which is plus 5 times 5 is 25 e to the minus x cosine 2x minus 45, 5 times 9 e to the minus x sine 2x. Okay, I think that's got them all. Let's combine like terms. Here we've got a 21. All the other parts are going to be the same. Talk about the cosines now. Here you got a plus 21, a minus 46, the other parts are still fine, and a plus 25. Okay, 21 and 25, sure enough, is 46 minus 46 e to the minus x cosine 2x. So sure enough, these add to 0. Now let's look at your signs. You have a 47 here, minus 2. That would be 45, and here you have a minus 45. So sure enough, those add to 0 too. So the differential operator that annihilates those are indeed the d squared plus 2d plus 5. Okay. All right. Now, let's do some other playing around with this. Sort of easy to get tied up in the mechanics of it and kind of lose the big picture. So let's do the best we can to maintain some of that. So with that deal that we just had, the alphas and the betas, and how these put together with your exponential with trig functions, sine and cosine parts of trig functions. Let's just imagine now that the alpha is 0. That should simplify things a little bit. N equal 1. So no multiplicity here. Okay? Then a special case of what we did before in the sort of tan box on the previous page, example 7, equation 7, would then be d2, and we did have a minus 2 alpha d, but alpha 0, so that goes away, plus the alpha is 0, so alpha squared goes away. Beta squared, okay? And we're letting it equal 1. So that's not, oh, I'm so sorry. Sitting in the cold, I'm sort of hunched over. Now all my muscles are stiff. So this is what we've got. D squared plus beta squared. That is your differential operator, okay? Operating on now I'm sorry, I can hardly breathe. Remember where your alpha showed up in the equations before were always in e to the alpha x. If alpha is 0, e to the alpha x is e to the 0, which is 1. So they've disappeared. And all you've got left are your cosine beta x's and your sine beta x's. Okay? So this operating either on cosine beta x or sine beta x is guaranteed to equal 0. Okay? Now, goodness gracious. For example, what if you had d squared plus 16? Okay? 16 is obviously 4 squared, so that would annihilate any linear combination of sine of 4x or cosine 4x. So you could have coefficients in there. So sorry. Call it C1 sine 4x plus C2 cosine 4x, or C1, C2, or any coefficients at all. So, sorry. I'm chilled in addition to being stuffy. Okay. Now, let's see. We are often interested in annihilating the sum of 2 or more functions, as we have seen in exercise 1. Sorry, I'm having trouble focusing my eyes. My head is so clogged up. My eyes are drifting on me. Okay. So we're often interested in annihilating the sum of 2 or more functions. As we've just seen in examples 1 and 2, if L is a linear operator, then L of y1 equals 0 and L of y2 is equal to 0, then L will annihilate the linear combinations C1 x1 and C2 x2. This is a direct consequence of theorem 4.1.2. I'm sorry, I'm having so much trouble focusing. Let us now suppose that L1, L2 are linear operators with constant coefficients, such that L1 annihilates y1, L2 annihilates y2, but L1 of y2 is not 0 and L2 of y1 is not 0. Then the product of the differential operators L1 and L2 annihilates the sum that is C1 y1x plus C2 y2x, okay, of x. We can easily demonstrate this, well, yeah, he's right, using linearity and the fact that L1, L2 is the same as L2, L1, which we noted earlier. And they do have a little proof or exercise in that. Exercise may not be the right word either. What if we had L1, L2 acting on the sum of y1 plus y2? Okay. Now the premise here is that L1 annihilates y1 and L2 annihilates y2. Okay. Now, start with, we just do distribute. And this would be L1, L2, y1 plus L1, L2, y2. Okay. Now, reminding ourselves, probably should have written down the other two. Goodness gracious. This is a fairly easy concept. It's just I'm having trouble even reading the page. All right. Because the linear operators are, and this comes from earlier, the we were just looking at it, and I cannot see it now. My eyes just will not focus. It goes back to theorem 4.1.2, but I don't think we actually have to go that far. Oh, here we go. No. Yeah, out there it is right there. L1, L2 is the same as L2, L1. They commute. It doesn't matter. So we can rewrite this as L2, L1, Y1 plus L1, L2, Y2. Pretty simple thing. But this right here, this is what we were given. The L of the L1 annihilates Y1. So basically, this goes to 0. And L2 annihilates Y2. That means that goes to 0. If both of those go to 0, then L2 operating on 0 is going to be 0. L1 operating on 0 is going to be 0. And this is indeed equal to 0. Okay? They say, for example, here, we know that from 3, which is back on the bottom of page 149, the D2 operator, the second derivative operator, annihilates any first order function, first degree function, linear function. For instance, 7 minus x. Doesn't matter what the function is, linear function D2 annihilates it. And from 8, which was the top of this page, that D2 plus 16 annihilates sine 4x, and pretty sure we see in 8 above that D squared plus 16 annihilates either sine beta x or cosine beta x, specifically sine 4x. Okay? Therefore, the product of the operators D2 times D2 plus 16 will annihilate anything that contains all that in it. The 7 minus x from the d from, I didn't write that down. It was that linear function, okay, and the d squared plus 16 annihilates sine 4x, okay? So this annihilates this annihilates sine 4x, okay, because we just saw above that it would. So therefore the product of those two would annihilate the linear combination of that, which it doesn't matter what you put, 7 minus x or any power of 7 minus x plus, and then any constant here, 6 times the sine of 4x. So if you multiply the operators, that wipes out the sum of the functions. If each of the functions were operated by a respective operator. Now, note the differential operator that annihilates a function is not unique. We saw in part B of example 1 that d plus 3 annihilates e to the minus 3x, but so will different operators of higher order as long as d plus 3 is one of the factors in the operator. Okay. All right, so I'm still having trouble breathing. So here's an example here. Let's go to a clean page. This is, again, sort of abstract, and you think what the point of all this is. It's going to get there, okay? This set of operators, d plus 3 times d plus 1 times, okay, that's one operator. Here's another one, d plus 3 squared, and d cubed times d plus 3. Okay? It says they all annihilate x to the minus 3, e to the minus 3x. All annihilate e to the minus 3x. Okay. Now it says verify that. Whew, goodness gracious. Well, they each have d plus 3 as a factor. And if you just go back to equation 5 near the top of the previous page, the d plus 3 automatically annihilates e to the minus 3x. Okay? This annihilates that. Okay? And since d plus 3 is a factor in each of those, it has to annihilate e to the minus 3x as well. Okay? And they say verify it, so I guess what we want us to actually do the calculation here. Okay? So let's do that first one. That would be d squared plus 4d plus 3. That operating on this, e to the minus 3x. Okay, let's just first do d operating on e to the minus 3x would be minus 3 okay, sorry. We're running a little out of time. Yuck! I just hit the wrong button. I meant to hit my erase key. I don't think I can go back. Sorry about that. Okay. I can't. Okay. I think my pen's operating again. Sorry about hitting the wrong button there. That was d squared plus 4d plus 3. Operating on e to the minus 3x. Okay. We did d of e to the minus 3x to be minus 3 e to the minus 3x. D squared of e to the minus 3x would be the derivative of that, which would be 9e to the minus 3x. Okay? So then we would have 9e to the minus 3x plus 4 times the negative 3e to the minus 3x. X. Boy. I'm so sorry. Plus 3 times e to the minus 3x. Let's see what this gives us. That's obviously 9 minus 12 plus 3. Yeah, that adds to that. Okay? Let's do the same thing with d plus 3 squared. That'd be d squared plus 6d plus 9. Operating on e to the minus 3x. And we've already done what those are, so let's just do them. D squared is 9. That'd be 9 e to the minus 3x plus 6, goodness gracious, times a negative 3 e to the minus 3x plus 9 e to the minus 3x. All right. Well, 9 and 9 is 18. 6 times negative 3 is 18. So that's pretty obviously the case too. What was the last one here? I'm really getting... Oh, d cubed times d plus 3. So that would be d to the 4th plus 3d cubed. Okay. Well, we only did the first two derivatives. Let's do the third one. D cubed of e to the minus 3x is equal to minus 27 e to the minus 3x, and d to the 4th would be 81 e to the minus 3x. All right, we're getting close to running out. Let's do this. That would be 81 e to the minus 3x plus 3 times negative 27 e to the minus 3x. And sure enough, this is minus 81 plus 81. That's equal to 0. All right, we verified it. As a matter of course, when we seek a differential annihilator for a function y is equal to f of x, We want the operator of lowest possible order that does the job. Okay, so typically that's what we're messing with. We are out of time, so we are beginning next time on undetermined coefficients. This is on page 151. Homework exercises include any of the odds 1 through 9, either 11 or 13 or both. I think you can do any of the odds 15 through 25. And I think we stop there, and we'll find the linearly independent functions after next time. Okay. All right. Sorry about the delays there. So I'm going to